absorption experiment. The purpose of this experiment is to remove CO2 in the air by using water. So the way this experiment works is that you feed water to the top of the column, and this packing here increases the retention time that the water stays in the column. So as the water falls down, you have air coming up, and they meet in the column, and they exchange the CO2 into the water, thereby removing the CO2 from the air.
Hi guys, my name is Wes Pride. I'm going to talk to you about the apparatus, the experiment we're working on right now. It's a distillation column. I'm a senior in chemical engineering, and I'll walk you through it. Back here we have a tank full of ethanol, which is ethanol or ethyl alcohol and water. And what we're doing is we're distilling that through this column. It's a packed bed or a packed column with these pieces of metal in it right here. They're lined all the way up. There's 6 of these inside this column. And so what we have is we have that coming into a reboiler. The ethanol comes into a reboiler on the bottom, and what that does is it heats it up into where it's into the vapor state. And when it reaches the vapor state, it's going to travel through all of those pieces, all of the metal packs right there, and travel all the way up to the top. It'll get to the top and it'll condense onto the condenser and condensate, and that'll trickle down right here into this. From what we do here is we measure we get little vials, we take a sample of everything, and we're measuring it over here on the gas chromatographs, which are right back here. And what these tell us is this tells us the overall percent of the water and the ethanol, and everything on the apparatus back here is run by pumps, which are controlled by this computer right here where Murphy is sitting. And from here we get temperatures of all of the different areas of our distillation column, as well as the levels in the reboiler and the condensate, and how hard the pumps are reading. So if you have any questions, feel free to come on by.
Good.
Hi, I'm William O'Mara, a senior chemical engineering major here at Florida State. I'm going to introduce you to our extraction column, in which we are extracting 1-propanol from hexadecane. After the 1-propanol hexadecane liquid-liquid mixture is fed to the column, the 1-propanol is extracted in the solvent, water, and falls to the bottom to our extract tank. The hexadecane is lighter, it rises to the top of the column and becomes our raffinate flow. By increasing reciprocating rate in this column and varying solvent flow rate to the column, we can monitor the factors and determine the output rates of our 1-propanol and our extraction rates from the hexadecane. We analyze these concentrations over here in our gas chromatographer GC, which gives us concentrations of hexadecane and 1-propanol in our flow rates.
Solid. This is experiment 445, and this is also known as the batch reactor. In this experiment, we are varying the concentration of sodium acetate and propyl acetate. So we have 2 different concentrations. So the trend you're trying to get in this experiment is that as concentration over time will decrease. So this is the trend we're trying to get. We're putting 2 doses of propyl acetate. So in the beginning we put a dose, the concentration will go down a little bit, and it's going to reach a steady state. Then we're going to put another dose to reach another steady state, and that'll be our final concentration, and reaction will have another thing important to note in this experiment is to keep track of the concentration throughout your experiment by doing your titrations and by calculating it during your experiment. If your concentrations vary to what you had in pre-lab, then you have a contamination and you should redo that trial.
Hello, I am Dylan Grice. I'm a senior chemical engineering student, and today we are operating on what is known as a continuous stirred tank reactor. It is what's known as a saponification reaction. We have 2 pumps which control 2 different chemicals which go into the tank and are mixed together, and they react at a steady state condition. This is my assistant, Taylor, my partner, not my assistant. Yeah, it's a very neat experiment. If you continue with the program, you'll get to learn more about it, hopefully. Thank you.
Hi, my name is Jillian Jones, and I'm a senior in chemical engineering.
Hi, I'm Becky Perrin, and I'm also a senior in chemical engineering. So this experiment is number 390, and it's called membrane separation. The goal of this experiment is to separate a pressurized air stream into an oxygen-rich stream and an oxygen-poor stream. Our hypothesis is that the oxygen will diffuse faster through the membrane than the nitrogen will. The feed stream enters the system through here and goes through a series of tubes to separate the oxygen. This is the oxygen-poor stream. This is the oxygen-rich stream. They can enter the volumetric flow meter to measure the volumetric flow rate of any of the streams. You can convert that to the molar flow rate by using the ideal gas law. This is the oxygen sensor. You can measure the composition of oxygen in each stream and read how much oxygen is in each stream on this sensor. The temperature of each stream can be measured on the thermocoupler reader.